Today's lesson will be on entropy, also in chapter 18 in your textbook on pages 568 to 570 if you're looking to reference your textbook. So I'm going to start off by just making this statement that probably right now your bedroom has a very high entropy. You probably don't know what that means right now. Maybe you do, but you probably don't. But by the end of this lesson, hopefully you'll understand why I made this statement. And so today, our lesson is going to focus on what makes a process spontaneous. Yesterday's lesson dealt with spontaneous versus non-spontaneous reactions, and today we're going to talk about why a process is spontaneous. It all has to do with disorder. And you'll see that I have a bullet point there that says disorder is the key. A process occurs because of increased disorder, and we call this entropy. And entropy symbol is a capital S, and entropy is a measure of disorder of a system. And the term entropy, just a little background, was coined by the German physicist Rudolf Clausius in 1865. And he used the term to describe the portion of free energy that is lost to the environment as waste heat. And Clausius pointed out that any process involving the flow of energy, there's always going to be some loss. And we talked about that yesterday in terms of our car engine not being 100% efficient, and even the processes in our cells not being 100% efficient. So entropy of the universe is continually increasing, meaning continually becoming disordered. So that term entropy was coined by Rudolf Clausius in the mid to late 1800s. So spontaneous reactions increase entropy or disorder of a system or the universe. So this kind of brings me back to that bedroom example that I mentioned to you at the start of the lesson. When you clean your room, everything is in order. So we could say that your bedroom, at that point, when it's completely clean and everything is in its place, we could say that your bedroom has low entropy. It doesn't take long, though, for your bedroom to get messy. Messy bedrooms have very high entropy. There's a lot more disorder in your bedroom. It's not easy to keep your room in perfect order. It takes a lot of outside intervention to keep your room clean. When I talk about outside intervention, I'm saying it takes a lot of time on your part to continually make sure you're putting things back in its place in your bedroom. So your bedroom is easily disordered or easily becomes messy. We could say your bedroom spontaneously becomes disordered or messy as well. So the natural progression of systems is to move in a direction of disorder or randomness, and we can talk about that in terms of something real life like your bedroom. Let's take a look at another example. On the left, the cards are ordered by number. So all the 9s are together, all the 10s, all the kings, all the queens, they're all ordered by their number. We could say that the entropy of the cards on the left is low because there's not much disorder. They're actually ordered in a very organized way. But if I drop those cards on the floor, and I actually do that in class, this is one of my demos that I do. But anyway, if I drop the cards on the floor, the entropy would increase. So if you look at the picture on the left, there's a lot more disorder in the cards. Some are upside down, the numbers aren't all together, everything's just kind of in disarray. And again, nature tends to spontaneously proceed to states of higher disorder. So if I went to pick up those cards, even if I pick them up and put them in a pile, and the pile looks orderly, they're probably not picked up by number and organized by number. So even if I pick them up and put them in a stack, they're not going to be organized. They're still going to be disorganized. So high disorder, high entropy. Nature has billions of ways to be disordered, but really only one way to be ordered. And the cards is a really good example. The cards could be organized in billions of ways, meaning they can be disorganized in billions of ways. But there's really only one way to order them by number. So hopefully that makes sense, looking at some real-life examples. So let's review the basics of spontaneity and entropy. Remember again that the symbol for entropy is S. So when you see that delta S, that just means change in entropy. So if I'm looking at a chemical reaction, do I have an entropy that's greater than 0 or an entropy in that reaction that's less than 0? So we'll be looking at those changes later on in this unit, not necessarily today, but just know that the S stands for entropy. So when S is positive, that means that we have a thermodynamically favorable reaction. It means that it's a spontaneous reaction. There's a lot more disorder going from reactants to products, and so delta S would be positive. So let me just write that out for you. The delta S, if I were to write this, delta S would be positive. That's what greater than 0 means. Now if I have a delta S that is less than 0 or a delta S that is negative, that means that the reaction's unfavorable thermodynamically, that it favors a more non-spontaneous reaction. And there's a lot less disorder in the products than the reactants. So a delta S that's a negative is not thermodynamically favorable. The next slides, we're going to cover some chemical examples of entropy increasing and show you what I mean by a delta S that would be positive or a delta S that would be negative. So here you can see an example of a phase change. So in that first Erlenmeyer, all the way on the left, you can see that I have a crystalline solid. So in this Erlenmeyer, I have a very ordered set of structure. Maybe it's a crystal of salt or something, a crystal of sugar, but it's a solid, and solids have very ordered structure in terms of their atoms and molecules. All of the atoms and molecules are very close together, and they don't really have a lot of room for movement, so very ordered. So let me just write that in there for you. So we have a very ordered structure here. Now if I look at the liquid in the next Erlenmeyer, you can start to see that the molecules and atoms have maybe pulled apart. They're all settling at the bottom of the Erlenmeyer, and there's a lot more disorder. They're not as ordered. So I've increased the disorder. So going from a solid to a liquid, I'm increasing disorder. So I'm increasing delta S. And you can see that increasing entropy here, that means delta S is becoming more positive as I go to the right. Now if I look at the last example, you can see that now the liquid has vaporized and it's a gas, and you can see the molecules are moving all over that Erlenmeyer flask, bouncing off the walls of the flask, and they're in great disorder. So we have lots of disorder in this Erlenmeyer. The most disorder, even more disorganized than the liquid, because they're moving around lots of areas where those molecules could be. So my delta S for sure here is going to be positive. So I'm increasing my entropy. Most likely my delta S of the solid would be negative because it's very ordered. And I went from very ordered to very disorganized or disordered. And so my delta S is going to increase as I move from order to disorder. On this slide, I want you to take notice of the glass of water that somebody is putting salt into. And again, we have that crystalline structure, or the salt crystals being put into a glass of water. So the crystalline structure, the purple and green here that I just boxed out, notice how it's very, very organized. So I have organization here. So when I have something that is this organized, my delta S here is going to be negative. As soon as it goes into the water, you'll see here that the sodium and the chloride ions have all kind of integrated and moved around all of the water molecules. So if I look at that dissolving in water, I can see that the molecules have become very unorganized or very disordered. So we have unorganization here. I'm running out of room on the slide. So unorganized. Anytime I increase that unorganization or I increase that disorder, my delta S becomes more positive. Now in this example, we're going to be looking at the amount of reactant molecules, or we could say moles. We're going to use the coefficients basically to decide if the reactant molecules, let me just write this out in the bottom, if the reactant molecules or moles of reactants are less than product molecules. And again, counting using coefficients. So let's take a look at the reactions that we have here. The first reaction is calcium carbonate, and it's a solid. So we've got something that's starting as a solid, and it's going to a solid and a gas, carbon dioxide gas, and calcium oxide solid. I'm starting with 1 mole on the reactant side, and over here I have 1 mole of CaO and 1 mole of CO2. So I have 2 moles on the product side. So my product molecules are greater than my reactant molecules. And because I have more molecules on the product side, I'm going to have more disorder. Now something else that I want to mention here too is I had a phase change going on. I started with a solid on the reactant side, but then it formed a gas on the product side. Anytime you see that phase change, it's going to automatically clue you in that you have more disorder. So this entropy change would be delta S that's positive, because I went from 1 mole to 2 mole, and I also went from a solid to a gas. So I had a phase change going on as well, causing more disorder. Now let's take a look at the second reaction, see what we have here. On the reactant side, I have a gas, SO3, and on the product side, I have gases being formed. So I can't really look at a phase change here. So here I really have to depend on the coefficients of the species that are reacting. So I have a decomposition reaction going on. So I have 2 moles on the reactant side going to 3 moles on the product side. So again, I have more moles on the product side. So this reaction has a positive delta S, or a delta S that's greater than 0, meaning there's more disorder. It means that it's thermodynamically favored, and it's spontaneous. And both of these reactions would be spontaneous, and they would be thermodynamically favored. If I went in the reverse for both of these reactions, then I would have non-spontaneous reactions, and I would have an entropy that is negative because the reaction is forming something that's more ordered than the products, if I went in reverse. The last example that I'm going to show you is an increased temperature of a system. So if I increase the temperature of something, that's going to make the atoms or molecules that make up that system move faster. So if they're moving faster at a higher temperature, and you can see down here we're increasing entropy and temperature. As I increase temperature, you can see in this last visual that the vibrations are becoming faster, and the atoms or molecules are found in a lot more disordered arrangements than if I look over here where the temperature was lower. Maybe say absolute 0, where everything's at rest and nothing is moving. It's in perfect order. So here, increasing the temperature, and this would happen in any system, increasing the temperature is going to increase entropy. So I hope those examples helped you understand what entropy is and increasing entropies in chemical processes, whether they be physical or chemical. So in your textbook, I told you that we were referencing 568 to 570. I would recommend reading that part of the textbook. There's other visuals in the textbook, as well as it just helping you take some good notes. And then I have a worksheet on the class page. It's an entropy worksheet that you can submit to the Dropbox. And again, that can be submitted as a picture or as a PDF. It doesn't really matter, but just make sure you handwrite your answers. I hope that you enjoyed that video and you have a better understanding of what entropy is. Again, your bedroom probably has high entropy right now. Probably not very ordered, especially since that has become your classroom.